Hello, welcome to everyone to my YouTube channel. So today I will teach about the basic, unique, basic reaction in organometallic chemistry. So in this class, I will teach about the oxidative addition and inductive elimination reaction in organometallic chemistry. So we have seen how neutral ligands such as the ethylene or CO can enter into the coordination sphere of a metal by substitution. So we now look at the general method for simultaneously introducing a pair of electron ligands, so A and B, by the oxidation addition of A and B molecules such as H2, CH3R. A reaction of get important in both synthesis and catalysis. The reverse reaction is reductive elimination, which to the extrusion of AB from the metal AB complex, and it is open product forming step in the catalytic reaction. So in the oxidative direction, we can break the AB bond and the from metal A and metal B bond, since the AB are the extra ligands. And the oxidative state, electron count conditions are all increased by 2 units in the reaction. It is in the change in the thermal oxidation state and give rise to the oxidative and reactive part of the reaction name. So that means in the oxidative reaction, the a metal A bond AB is broken and it is directly connected to the metal. So here in the oxidative addition, the oxidation count of the metal is increased by 2 unit, and the coordination side also increase the 2 unit, and total electron count also increased by 2 units. So here from here it is suppose is 16 electron complex. So here it is a 8 electron complex, and the reductive elimination is the reverse one. So in the reductive elimination, the oxidation state is decreased by 2 unit, and the coordination number decreased by 2 unit, and the electron count is decreased by 2 units. So the oxidation for addition proceed by a great variety of mechanism, but the fact that the electron count increased by 2 units means that a vacant electron site is always required on the metal. So that means for the oxidative reaction, the metal should be as coordinately unsaturated. So a vacant 2 electron site is always required. So we can either start with the 16 electron complex, or a 2 electron site must be opened in the 8 electron complex by the loss of the ligand. So the change in the oxidation state means a metal complex of a given oxidation state must also have a stable oxidation state 2 units higher or under the oxidative addition. So that means when in the oxidative addition, the metal oxidation state is increased by 2 units. So that means that oxidation state of the metal should be stable. That then the oxidative addition will occur. So in this equation, in the equation 6.2 shows the binuclear oxidation addition in which each of the two metals changes oxidation to state, electron count, coordination number by one unit. That means here in this case, both the metal oxidation state is increased by 1 unit, and the coordination number also increased 1 unit. Electron count will be increased by 1 unit. So it is a binuclear oxidative addition. So this typically occurs in the case of the 7 electron complex or a binuclear 8 electron complex with the MM bond, where the metal is stable oxidation state more positive by 1 unit. So binuclear oxidative addition is happen when the metal is a 17 electron, or in the metal is the 8 electron, and metal bond is formed. So metal has only the one positive unit oxidation state, stable oxidation. At that time these things happen. So in this table, different type of more common types of oxidation reaction by DN configuration and position in the periodic table. Whatever the mechanism, there is a net transfer of pair of electron from the metal to sigma star orbital AB bond, and of the AB sigma electron to the metals. So some examples, suppose is a D7 to D6. So here cobalt 2 to cobalt 3, the binuclear oxidative addition. So the clips of the AB bond and the next and Ma or MB bond, the reaction is promoted by starting with a metal in reduced state. So only rarely do the metal in the oxidation state have been passed to return sufficient reducing character to undergo oxidative addition. Expect with the powerful oxygen like Cl2, conversely, high oxidation oxide metal is more likely to undergo reductive elimination. So that means the class 2 oxidation state is not energetically favorable for to achieve for all type of metal. So the powerful oxidation oxidizers like Cl2 will give this type of conversion. So and also the conversely high oxidation state of metal is like to undergo reductive elimination. So as we have seen, the oxidative addition is the inverse of the reductive elimination and the vice versa. So in principle, this reaction is reversible, but in practice, they tend to go in the oxidation or reduction direction only. The position of the equilibrium in any particular case is governed by the overall thermodynamics. So that means in theoretically, oxidative addition and the reactive elimination is a reverse reaction. So, but in principle, there is no equilibrium. So only one type of one direction is formed. So that equilibrium is governed by the overall thermodynamics of the reaction. So that in turn depends on the relative stability of two oxidation state, balance of AB versus Ma or Me bond strength, and alkyl hydride complex commonly eliminate alkane, but only rarely do alkanes oxidatively added to the metal. So conversely, alkyl hydride commonly added to the metal complex, but the adducts rarely reactively eliminated in the alkyl hydride. So that means alkyl hydride complex commonly eliminate the alkane. So here alkane molecule is reactively eliminated from the metal. So here the elimination of alkane will favor the reaction in the reactive elimination, but the oxidative addition of alkane is not happened. So it is not a thermodynamically favorable process. So that's why only the reactive elimination to form the alkane is happening. But for the alkyl halide case, it commonly do the oxidative addition, not the reactive elimination. Here, so that's why the stability of the molecule will favor the overall process of this reaction. The third flow elements which tend to have stronger ligand bonds tend to give more stable adducts, occasionally equilibrium established in both forward and backward direction are observed. So reaction in the oxidation direction is usually favored by strongly donor ligands because they stabilize the oxidation state. So that means when there is a more electron-rich metal center, that will favor the oxidative addition reaction. So while the formal oxidation state change always 2 units, so the real change in the metal such less that because of the AB don't end up with a pure -1 charge. In LNP, the change in the real charge depends mostly on the electronegativity of A and B. So the following region are more oxidizing in order. So this is the order of the oxidative nature H2, HCl, and Cl2. So we can estimate the oxidation power of different region experimentally by measuring the mu CO ongoing the iridium CO and Cl2, because the more oxidizing region will reduce MO back bonding and make the mu CO is a more negative. So that means in oxidative addition, the net +2 oxygen in the oxidation water metal do not happen. It depends on the oxidation power of the molecule. So here we can calculate. We can estimate the oxidation power of different region by the simple sigma mu CO of the carboxylating frequency of the adduct. So these reactions are not limited to the transition metal. Perhaps most of the familiar oxidation is formation of different regions, but it can occur whenever the element has 2x7 oxidation state by 2 units apart. So equivalent here the oxidation to P3. So here this is not the only for transition metal. So here the Cl2 is oxidative addition to the PCl3 to form the PCl5. Here for the manganese is 0 oxidation state, here manganese is 2 oxidation. So this is also an example of the oxidative addition. So in this table, carbon splitting frequency of the oxidative addition product of the Vasta complex. So here, in this range, the oxidizing nature of this molecule will increase. So when it will connect to the metal center, the mu CO of the complex will staging frequency increase due to the net positive charge on the metal center. So the more less electron density, that will discover the band bonding to metal to carbon. So here, when Cl2 is attack, it will form more positive sigma mu staging frequency. So that means for Cl2 case, more the shifting of the staging frequency. So this is proof that Cl2 is a more oxidizing in nature than other complex. So usually the feature of the oxidative addition reaction of transition metal is the usually wide range of reagent AB that can be ignored, including such a non-normal relatively unreactive molecules silanes, H2, and alkanes. Oxidative reagent vary diversify mechanistically and will therefore for each type of the separate group. So oxidation reaction can do with the simple hydrogen or even alkanes or silanes. So first we discuss the concerted addition. So concerted or three-center oxidative addition is really the associative reaction in which the incoming ligand, for example, the hydrogen was first bind to the as a sigma complex and then undergo H2 bond breaking. As a result, near strong back donation from the metal into the sigma star orbital and non-polar regions such as hydrogen or compound containing CH or silicon hydride bonds are all tend to break via the transition step or more probably the intermediate of this type. So step A. So here is a possible mechanism. So in the step A, here in the step A is the association step. It involves the formation of the sigma complex. Sometimes this is a stable and the reaction stops. Here B is the oxidation part of the reaction. B is the oxidation part of the reaction. Is which metal electrons are formally transferred to the sigma star orbital of the AB. So here that means the concerted mechanism. First the molecule is bind to the metal center as a sigma complex, and then the electron transfer from metal to sigma star orbital of this molecule. Then the bond breaking happen, and this oxidative addition product was formed. So base studies in the case of addition of the H2O in the 16 electron planar Haskell complex, radium Cl COPPH2 to give a 8 electron D6 octahedral diiodide complex. Normally, two ligands that are in the trans in the iridium 1 complex fold back to cis dihydride isomer, but subsequent rearrangement can occur. Conversely, a reductive elimination such as the loss of the H2 from dihyde, the two ligands of the eliminated normally to have the cis to one another. So here the first square planar complex, the addition of the sigma complex, that is a trigonal bigonal electron complex, and then this H2 is a stance manner to form this octahedral 8 electron complex. So in the oxidative addition H2 to Haskell complex, the trans ClCO sets of ligand usually fold back to become a cis in product. So cis in products, the alternative product with the phosphine foldback is rarely seen. As a powerful pi acceptor, the CO prefers to in the equatorial plate, resulting as a TVP transition state, which may resemble intermediate H2 complex 6. The tendency for a pair of trans pi ligand to fail back can also strong that cigar planar D8 M2 starting material already strongly distorted even in the absence of the incoming ligand. So such case trans CO to wherever two pairs CO fold back strongly, as we saw in the high trans effect, ligands such as CO prefer to be equatorial TVP. In this case of TVP-like geometry, one might suspect that the steric bond of the phosphine could play a role, but theoretical. So here, for this ligand, the CO ligands in the transposition fold back due to the higher steric bond of the phosphine ligand. So here, this is a TVP-like structure. So a 2 electron side must be present in the metal for reaction occur. So in the 8 electron complex, the ligand dissociation must take place first. So the reaction, so that means for the oxidation addition, 2 electron second side must be present, and for 8-electron complex, ligand dissociation must be occurred to do the reaction. It is the dissociation in nature. The reaction are very usually second order and slow negative entropies of activation of constitute the order transistor such as 6-1. They are the little affected by the polarity of the solvent, but also extended some reaction by electron releasing ligand. So the CH and silicon hydride bonds of various hydrocarbon and silane can oxidatively added to metals. Among the different types of CH bond, those of arenes are particularly prone to do this because of the high thermodynamic stability of aryl halide product. So agnostic complex, sigma complex of CH bond can be thought as a lying along with the pathway of the oxidation, but arrested at a different point. A study of the structure of a series of these complex allowed to kinetic pathway. So this is the general strategy for studying reaction trajectory. The CH bond seems to approach with the H atom pointing toward the metal, and then the CH bond pivots around the hydrogen to bring the carbon closer to the metals in the side of the arrangement, followed by CH bond complex. This addition goes the retention of the chemistry of the carbon and expected from this mechanism. So here, when the CH bond is added, CH bond is oxidative addition to the metal center. So first, the metal hydrogen is come closer to the metal. Then there is a metal hydrogen bond interaction. Then it favor to come the carbon atom closer to the metal center with the retention of the stoichiochemistry. So the carbon-carbon bonds do not normally oxidatively add, but in classic aldehyde case, the reaction of the cyclopropane with the PT2 to give PT5 metacyclopropane. So illustrate how the reaction was driven by the resistance. So biphenyl readily reacts in same way. In the example, high turns effect to the resulting biphenyl ligand make this selective additional therapy geometry in the spite of the normal difference of electron oxide in 3. So here, normally the carbon-carbon bond do not oxidative addition, but here is a so here is a example where PTCNT in the cyclopropane reacts with the PTCNT from this intermediate, and this is the PT4 product. So here also the biphenyl ring oxidative addition to the iridium center. So when Haska complex when the Haska complex add to a oxygen molecule, the metal reduce the oxygen to O2 minus. So the peroxide ion who is coded to the iron 3 to give 6.1 from the 6.4 equals. Why not the increase the reaction in the ligand addition of reducing O2 as a 2 electron such as so it is the same problem we look in the result of the different formal oxidation state assigned for L and X2 in fixed extent to have the binding. So in fact the ethylene is much closer to the LX3 as seen in the reaction while the O2 very close to X2 So that means that the conventional description of the ethylene binding as a ligand addition or simple substitution and O2 binding as a oxidative addition are the most appropriate. So for ligands such as a CF2CH2 which bind in a fashion that is approximately equidistant between the two extremes. So there is a clearly gray area in which the choice between the two description arbitrary. They emphasize that the category as oxidative addition where the metal construct have the limitation. So here that means the ethylene which is a L2 type ligand which directly adding to the metal center. So it is not the oxidative addition, but in case of O2 it is likely the X2 type ligand. So that case the oxidative addition reaction occur. So here the O2 is react with the Haska complex to form this peroxide attack. So aryl halide can also react via the coordinate concentration mechanism. For example, the PDPR and healthy will react with the ERBR in this way. The periodic loss of PAR3 is required to give the reactive 1 intermediate, which reacts to aryl to give this as a bifinal product. So next we will discuss about the another type of oxidative addition, which is the SN2 reaction. So in all oxidative addition, a pair of electrons from the metal is used to break the AB bond in the reagent. So in the SN2 pathway, adapted for the polarized AB substance such as alkyl halide, the metal electron pair of the Ln2 directly attacks the AB sigma star orbital by a inline atom at the least electronegativity atom, formally give the Ln plus 2 and A minus and B minus fragment are on the ionic model. So that means for the SN2 mechanism, the direct attack from the metal to the sigma star orbital of this AB molecule. So AB molecule here, so suppose the polarized molecule such as the alkyl halide. So SN2 mechanism is often found in the addition of the methyl, allyl, acyl, and the benzyl halides to species such as the Vasa complex. So like the concentrated type, they are the second order reaction, but they are the accelerator in the polar solvent. So the negative entropies of the activation. So this is consist with the ordered and polar transition state in the inorganic SN2 reaction. So that means if this reaction goes by a polar transition state, which is favored in the polar solvent. So here the net negative entropy activation. So insertion of the carbon is found to suitably substitute halide. So here the stoichiochemistry of the carbon of the oxidative addition products are determined the carbonylation to give the metal acyl followed by the methanolysis to give the ester. Both of these reactions are known to leave the configuration of carbon unchanged, and the configuration of this ester can be determined by the measure of the optical rotation. So Rx may end up with C or touch to one to another in the final part as expected from the recombination of the ion pair formed in the first step. So equation case when is the product in the strands, this happens because the high transfer of the ethyl group prefers to remain trans in the vacancy of the cisgender perimeter intermediate shown in the treatment. So that means when the metal is attacked to the alkyl halide, so here the retention of the stoichiochemistry of the carbon center, and here the trans setup is favorable in the SN2 mechanism. So of these two types of first involve the oxidation of the two units. So here these are two-step reaction. So here first involved in the oxidation addition by two units by no change in the electron count. So N plus is a zero electron region. So here this is the change in the electron oxidation state of the metal by two units with a zero internal electron count, and second involved is increase the two electron count but no change in the oxidation state. So only these two steps together constitute a full oxidative addition. When the 18 electron complex is involved, the first step is therefore possible without the necessity of the original ligand force. Only the second step requires a vacant reference site. So in some cases, the product of the first step is stable, does not lose the ligand to admit the allied anion. It is sometimes loosely called the oxidative addition, but in the concept is the electrophilic attack to the metal. So the more nucleophilic the metal, the greater is the reactivity of SN2 addition. So that means more the electron density in the metal center, that will favor more the SN2 mechanism. And stirring heat gens. So this is the for the nickel zero case. This is the order of the oxidative addition of the metal center with the increased electron density. Also the stirring index at the carbon. So the reaction in the reactivity of the order is the methyl iodide, ethyl iodide, isopropyl iodide. So that means steric crowding of the carbon center will be also favor the rate of the reaction. So for the methyl iodide case, the reaction is usually faster. And the beta leaving group at X at carbon accelerate the reaction. So this gives the reactivity order of the this mechanism. So also the reactivity of the leaving group, the oxidative addition rate of the oxidation reaction will depend. So halide ion can increase the nucleophility of the metal. Hence, the expert in the powerful catalytic event, the SN2 oxidative addition, such as an effect is seen. For example, the iodide ions in the oxidation of methyl iodide to rhodium iodide COPPSC to give the rhodium Me2 iodide is initially replaced the BPSC in the metal center to give the intermediate and reduce rapidly the methyl iodide. So alkyl Another reason is strong tendency to the give SN2 addition to give the following rapid reversal addition of the addition equilibrium. The next one I will discuss about the radical mechanism. So in the radical mechanism, in oxidative addition, I will recognize later than the SN2 and concentrated process. A troublesome features of this reaction is that the minor change in the structure of the substrate of the complex are included within the reaction. So solvent can sample enough to change the rate of even the predominant mechanism of the given reaction. They can also be photo-initiated. The sharp disagreements have turned on the question repeatedly on what type of experiment evidence should be considered as a valid mechanism criteria. For example, the use of the radical taps such as a nitroso has been criticized on the ground that there are many these illicit radical pathways for the reaction have otherwise formed non-radical mechanism in action of trap. So two types of radical process are now distinguished: the non-chain and the chain. The non-chain variant is believed to operate in the addition of a certain alkyl halides. So here, first the reaction ligand dissociation, then the formation of the radical, then the alkyl radical will form. The alkyl radical which is to form the oxidative product. And the key feature of when some on-rate transfer to metal to alkyl halide to sigma star to form N plus and the Rx minus. After that, the X minus transferred to the N plus and the R dot radical is liberated. This produce the pair of radicals which rapidly recommends to give the adduct before the either they can escape to the solvent case. Like the SN2 process, the radical mechanism was faster, more the basic metal and the more readily electron transfer takes place. So that gives the reactivity order of the alkyl iodide and alkyl chloride. So unlike the SN2 process, the reaction is very slow for alkyl prosylate. It goes faster as the alkyl radical become more stable, so easier to form. So giving rise to the order R group is the methyl. So here for the radical mechanism, the more the stable the radical, that will favor more the faster reaction. So the tertiary carbon will be more stable, that will give the more easier to form. So in the reaction is the nickel Li3 with the iodide, the nickel complex in a LXL3 formed as the first step is sufficiently stable to survive, and as the observed product in the reaction, the air radical abstract the hydrogen atom from the solvent to give the aryl ARA. So there are also separate cases where the organic radical is sufficiently stable to survive and become the product of the reaction. For example, reaction of certain quinones with the NiH3. The second general category is the radical reaction is radical chain. So this has been identified in case of the reaction of ETBr with the PHCH2 with this PME3 analog of Vector complex. That can lead to a chain process if the radical form can escape for the solvent case without recombination. Otherwise, the radical initiator may be required to set the process going. This can be lead to interaction period. In either case, the metal center radical abstract X dot from the halide to leave the chain carrier R dot. The chain carrier termination steps such as limit the number of cycles possible per R dot. The alkyl groups always lose the anisotropes at the alpha carbon. Unlike the non-chain case, the reaction slow down or stop in the presence of radical inhibitor, as the phenol process diamond which are to form this RH. In the stable, therefore, the unreacted oxyradical reactor. So here the chain mechanism. So R will first get with this to form this complex. Certain substrates are particularly useful for determining what happens to the stereochemistry at the alpha carbon during the oxidation addition in other reaction. For example, we can obtain the defined relative stereochemistry at the alpha beta carbon. This is the advantage. We do not need to resolve anything. We have both enantiomer present, but the associated reaction will do nothing to stereochemistry of the beta carbon. So we can look at the configuration of the alpha carbon position because the beta carbon. This is easily done by one spectroscopy. The transformation or the substitute two bulky ligand, bulky groups, tartrate and MLN. Tartrate and X are anti to one another. These are both the alpha beta position cause or anti to the one another according to stereochemistry of alpha position retained or inverted. So by the curved relationship, you tell this CH dihydrogen from the observed very different coupling constant. Phase 2 survey iron chemistry, for example, so the product is equal to X. So other useful test of the radical rely on the fact that some free radicals are known to rearrange very rapidly. So for example, in hexanyl bromide gives the cyclopentyl methyl metal complex, then a radical intermediate is strongly indicated. Cyclobromide methyl radicals on the other hand reagent to give opening to give this radical. Another common reaction of the radical are the Cl2 abstraction from the coordinated solvent to give the RCl. The timer is to give the RR bond. So NMR method called the chemical induced dynamic decomposition can be useful to certain cases. This method relies on the fact that the product of the radical recombination can have very unusual distribution of alpha beta spin. This implies that the 1H NMR may slow the large positive or negative peaks if the coordinates are right. It is not easy to tell how much reaction is involved. So here, this molecule, here the radical mechanism, here the radical is formed. So they will recombination to form this cyclopentyl intermediate, and then this product is formed. So binuclear oxidative addition, because they involve one electron rather than the two electron changes in the metal. So open go via radical. One of the most common example is the COCN5 which react with the RX to form this intermediate. The red determination is the main abstraction of the halogen atom from the RX by the odd electron D7. The reason occurred combined to second covalent center. So in the reaction involved radical, it is important to use the solvent that don't react with the first with the R dot radical. So next one we will discuss about the ionic mechanism. So hydrogen halide are open related largely distributed on solution, and the anion and the cation tend to add to the metal in the several steps. So two variants have been recognized. So more common example, the complex is basic enough to coordinate it, which the anion binds to give the final product. Rather in the opposite case, with the halide ion attack first, followed by the potential of the intermediate. So first route is favored by basic ligands and the low oxidation state of the metal, and the second by the electronegative ligands and the need positive charge on the metal complex. So this polar solvent enters both types. Example. So in the ionic mechanism, here these are reacted in dissolved in the solvent from this H plus and Cl minus that will pass the positive charge in react to form this complex. Then the Cl minus is subsequent elements of PPSC from this product. The rate of the first step is typically follows the this equation. The resistance of protonation in the source step. This can be carried out independently by using the acid with a non-bonding anion such as HPF4 and HPFC are most commonly. The anion is insufficient decomposition to carry out the second step, so the intermediate can be isolated. This is an example of general strategy in which the non-bonding anion is used to the isolate reactive cations to the stable state. So the rate of the second type is usually follow the rate equation. So in the second type is follow this rate equation, which can be step can be carried independently without the LICL alert, but no reaction observed with the HBF4. This is the cationic iridium complex is basic enough to coordinate HBF4 minus with the non-coordinating anion. So other acids which are ionized to see substance into the solution, such as RCO2, HCl2, may well react by the same mechanism. But this is not the yet be noted in detail. So in this alkyls are often clipped with the acid to give the alkane. In some cases, the simple protonation of the metal to give these hydride positive intermediate or MR bond to give sigma complex is like mechanism, but in others there is a dependence on the rate of the some cases even the product. So on the counter case, the oxidative addition and reactive addition mechanism is more likely. So here the platinum R2 pairs to react with the HCl to form this intermediate, then subsequent elimination of the alkenes body, so form this product. So in summary, oxidative addition increase both the oxidation state and the oxidation number by 2 units, and the oxidative addition can go by the different mechanism, or maybe the ionic mechanism, mechanism, or radical mechanism. So, thank you.